Okay, welcome to this tutorial on how to register in vivo to ex vivo images for systems neuroscience. Um, so we're going to be going through to see how to register a bunch of microscopy images to each other using this tool called CASTalign. So I'm going to talk at you for a little bit on some of the basics that you need to know, and then we're going to go ahead for the interactive demos. So if you've already read the tutorial online, you can probably skip ahead to those demos. Okay, so first, what is the purpose of any of this? So CASTalign allows us to register different volumetric microscopy images to each other, and it allows us to manage kind of lots of these big sets of transformations between images because we'll usually have a lot of images that we want to align to each other in a typical experiment. So this can include things like in vivo z-stacks, ex vivo sections, and then also aligning in vivo two-photon to ex vivo confocal, or things like this, in vivo to ex vivo, where you're often going to have a lot of warping, a lot of complicated transformations, and we need to be able to link these all together. So there are three main concepts to go through with this. So the first is the idea of transforms. The second is the idea of graphs. And then finally is the graphical interface that we'll work through. So transforms in general, I mean, here's kind of a more formal definition, but they just get you from one coordinate space to another. So if you think of different images as different coordinate spaces, you want to map coordinates in one to another. This can be images, it can be points, and anything can be a transform as long as it's, at least in this library, anything can be a transform as long as it's an invertible function. That's the key because we need it to be invertible for it to work. So some examples. So down here, we're going to have the Python code of how you might do something like this. This is all pseudocode. We're going to import CASTalign as CA. So whenever you see CA dot something, that's going to refer to CASTalign. And then this image is, we're going to load an image over here, and we're going to do this to the image. So if we want an identity transform that doesn't do anything, we're going to do import CASTalign, whatever, transform equals the identity transform. And then we can just call the transform as a function with the image as the argument. And that'll give us out the same image, which isn't very exciting. But if we do something like translate, this starts to get a little bit more exciting. So we can define this. These are all affine transformations. So we can define an affine transformation where we have a shift of 50 in x and 40 in y, and we can transform the image, and it's shifted. We have a bunch of other ones. So we can rescale. We can rescale it in x and y. We can apply a shear. We can do that as well. We can also do nonlinear warping. I'm not going to talk about this right now, but we'll get into that in the second half of the tutorial. We can also do rotation. So here we just take this image and we rotate it. We can also invert all of these transforms. So if we take that rotation example, we can just call, so we make the transform as affine parametric, z rotate is this. And then the inverse transform is just t.invert. And then we can call that inverse transform just like we would any other transform. So you can think of these transforms as just objects that you can play around with and do stuff with. We can also join them together. So if we have transform 1, and that's maybe a rescaling, and then transform 2 is a rotation, we can just take our final transform equals t1 plus t2. So that takes this image, it applies a rescaling to the image, and then it rotates the image. Just doing t1 plus t2, that composes them together. And so it does this losslessly, well, only with one resampling step. So you should know too that transforms, of course, these are not commutative. So if you apply the rescaling first and then the rotation, you're going to get a different result than if you apply the rotation first and then you apply the rescaling. So the order does matter here. But also this is, these are, you can chain these together like we've been doing, but it's also lossless. So normally what you might do is you might, if you weren't using this library, you might apply one rescaling, or you might apply one transformation, and then you'd apply another one right afterwards. And if you do that with something like rescale, this is the most obvious example of this, you're going to get a pretty big loss in quality here because we've shrunk the image down and then we've scaled it back up again. But actually, if you do all of this by chaining transforms together in CASTalign, you don't have to worry about this. So for instance, in this rescaling, we rescaled it down 10 times smaller and then made it 10 times bigger. And so we're doing that here, and this actually just ends up being the identity transform. And we have no loss in quality, even though we've scaled this down and scaled it back up, because we're doing these as composed transforms. Okay, so that's how we transform images. What about points? So here we can load points. Let's take our trusty identity transform that we used before. And if we just have these 2 points that we want to map from here to here, the identity transform doesn't do anything with them. We pass, so just like we passed before, transform with the image, we can just pass the points directly as function arguments to this transform object. And we map these 2 points, we map them straight over here. Because it's an identity, it doesn't do anything. But maybe in a more interesting case, if we had a rotation, we can take the original image and we rotate it. And now that it's rotated, we have this point here and we have this point here, and they map to the same original places. So this is, again, just by taking our points and passing them through the transform object. And they rotate along with the image. So all of these that we've seen so far, you have to manually specify the points, manually specify the parameters that you want. You can also use CASTalign to learn these transforms from pairs of images, and that's what we'll be doing most of. We'll be doing that a lot more in the second half. You'll need the graphical interface to do this, so I'll explain that a little bit more in a bit, because you have to use the graphical interface to select the different points. But you select the points in image A, you select the points in image B that you want to correspond to each other. And through these pairs of points, you can learn a transform. Okay, so this is transforms. Now let's look at graphs. So graphs allow us to organize large quantities of transforms together along with their images. So usually in most data sets, you're going to have a lot of different images. So for instance, here taking an example, we have a z-stack that we take on the day, so our daily z-stack. And then we have a lot of individual planes. So these are calcium imaging planes that are registered to the z-stack. And then we have a reference z-stack. And so we want to register the daily z-stack to the reference. And then we have a different color of the reference, which we can register. And then also we have individual sections. And these sections are our ex vivo sections. So all of this is in vivo. And then these two are ex vivo. And we can register these together. And then the different colors of the section can be registered together. So we have a lot of different images that we need to be registered together. Each of them are going to be registered together with a different transform. And so this forms these big networks, these big graphs of different transforms. And you can create these graphs within CASTalign. It'll compress the images for you. It's usually like 100 to 1,000 times compression ratio. Without much loss in quality. So you can construct these graphs and easily go back and forth between them. So that was a simplified example. This is a real example from some of my data, so they can get pretty complicated. A lot of these, by the way, I should mention, are automated, so they don't require any user input to generate most of these edges in the graph. But just to hammer home again, in this example of the graph, each of these blobs right here is an image. So each of these nodes is an image. And each of these arrows, each of these edges is a transform that takes you from this image to this image, or from this coordinate space to this coordinate space. And then from this coordinate space to this, or this one to this. So here's an example of if we want to use a graph. So we can just load the graph with CASTalign.load. And this is an example graph I'll be showing you for this demo, where we just have a z-stack, we have an image, and we have a transform, which we're calling T1, which links them together. So if we want to, so once we've loaded our graph, if we want to get one of the images just as an image file, as a volume, as a 3D image file, you can just you can use these square brackets to get the image, to load it. If you want to load a transform, you can also use these square brackets, except instead of just passing the name of the node, you pass the name of the first node that you want, and then a colon, and then the name of the second node. And that'll get you from, so this will be the transform going from z-stack to image in this case. If you want to add a new one, so let's add image scaled. Let's scale it up by, I don't know, a value of 10 times. So we can add, we can multiply all the values of image by 10, and we'll add it to a new one, which we're going to call image scaled. And so that's a new node. It's not connected yet, but we can connect it. So like here, we're just going to connect it with an identity transform. So we do that. We use the same notation of going from image to image scaled, and we're going to connect them with a identity transform. And finally, this is the real powerful thing about using graphs, is not only can you keep all of this information together, but you can automatically compose transforms together. So here, if I want to go from the z-stack to this image scaled, I don't have a direct connection there, but I can just ask for it. So I'm using the same notation I used up here to ask to go from the z-stack to the image scaled, and it'll give me that, and it'll construct this by composing this transform with this transform, and it'll give me this transform going all the way. So when you have a graph like this, that means you can take, for instance, we can take, I don't know, plane 4, and we can overlay plane 4. We can transform this to the space of section 1 red, or maybe section 1 green. So we do that by just asking for it. We could just ask for plane 4, which will take us to the daily z-stack, which will take us to the reference, and then to this. So it'll just compose all of those together in a chain using the shortest path to get there. And then we can immediately have a transform to get us from here to here, which means that we can visualize this in the same space as this, or actually more usefully in this case, we can do the opposite, and we can go from section 1, or the segmented version of section 1, to doop, 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 and right over here. And we can see where all of the segmented cells from section 1 line up with the segmented cells from plane 4, even though this is in vivo and this is ex vivo, and we have no direct connection between them. And this is obviously extremely useful when you have a graph like this. You can just choose any of these nodes anywhere, maybe this node, and you can say, take me there, and it'll just automatically find the path that'll get you from, I don't know, I lost it, somewhere around here to somewhere around here. So this can be extremely useful in managing these large data sets. Okay, so lastly, we're going to chat about the graphical interface, and then I'll show you how it's used. So with the interface, so let's load a graph. So we've seen this before, import CASTalign. We also have to import CASTalign.gui, and that's just because this imports a lot of libraries, and you might not want to install those on a headless server. So we can import this, we can load the graph. I'll distribute this file so that you can follow along. This workshop graph, oh, sorry, that should be workshopgraph.db, not .mpz. Workshopgraph.db. So we're going to load that, and this is what we're going to get. So we're going to have these 3 different components that aren't going to be connected. So we're going to have something called daily z-stack. So this is an in vivo z-stack from two-photon calcium imaging. And these are a bunch of planes also from two-photon calcium imaging. We're going to have this other one, which is where we have a reference z-stack right here. And we're going to have a red version, and then this one is the green version. And we're going to have that already registered to section 1, just as a demo to make this easy. And then second, we're going to have this section that we haven't registered yet. And this is the one that we'll register together. So we're going to do a couple things together. So first of all, we're going to register the daily z-stack to the reference z-stack. And this is the command we're going to use to do that. So just this align interactive, daily z-stack to reference using graph G. And again, we can just refer to the nodes here, the names of the nodes, or the names of the spaces, or the names of the images, or whatever you want to call them. So we have the daily and we have the reference, and we want to align those together in the context of graph G. And the other one we're going to do is this one. So then we're going to register the reference z-stack to section 2. And so we're going to, this is all, everything that I'm circling right now is all in vivo. Or actually, no, these sections, these are ex vivo. This is in vivo, this is in vivo, this is ex vivo, and this down here is ex vivo as well. And so this is the command we're going to do that. So I'm going to walk you through this command quick. It's very similar to this previous one, except instead of going from, we always use the from to syntax. So, or the order. So the first one is always going to be from, and the second is to. So we're registering from the, oh, actually I have this backwards. No, it should be the other way around. We're going to register from section 2 green, section 2 red. Sorry, this command is wrong. From section 2 red, section 2 green. So this is our first chunk. So if you put these in brackets or parentheses, you can group multiple of these together, so then you can move them around and work with them as one chunk. So we have this section with the reference. We have the graph G in this context, and we're going to start with section 1. So we're going to start this transform right here, and that just gives us a starting place. Because we know, I'm telling you right now that these sections are next to each other. They're actually tiles on the same section, technically speaking. So from microscope confocal tiles right next to each other. So they're going to be close to each other. So that'll give us a reference point. And since we're sectioning these sections next to each other, we always know they're going to be close to each other. So we can use one of these already aligned sections as a reference. So we're going to start with that. And then references over here. So actually this should probably, instead of start, should be transform equals. Sorry, there are lots of typos in this one command. So transform is going to be section 1 green. And then references. So references are ones that we just want to see. We want to see where they are because it might help us align. So you might want to list as references ones you've already aligned that are nearby that you can use as just reference points for how to find where you want to go with the current section. Okay, so this is all we have now. So now we are going to switch over to the live demo. So in this demo, we're going to walk through some of these commands that we've seen, and we're going to use them to do a registration. So let's start out. So let's import CASTalign. So CA, and then we can import the graphical user interface like we saw before. So right now I'm just running all of the commands that we saw in the previous slide. Well, I'm gonna fix the ones that were wrong. Okay, so graph equals ca.load workshop graph.db. Okay, so now we have it loaded, and we can visualize it. So graph.visualize, and it's going to show here. And so this is what we just saw before. This is what it looks like. We have the daily z-stack over here. Over here we have the reference, and down here we have the sections. Okay, so we've got that. So now let's do our first alignment. So we can do ca.gui dot align interactive. And what we want to do is we want to align the daily z-stack to the reference z-stack. So we'll start with the daily, and then have the reference second, and then our graph is G. So we're going to run this, and up pops this window. And this window allows us to choose what kind of transform we want, because oftentimes we're going to want to chain them. So this allows us to build that chain. So let's start with, rigid is usually a good place to start. So let's start with rigid. And if we do rigid, we're going to, we have this Napari window come up. And we can go and we can have a look around here. These are what the z-stacks look like. So let's start by just moving them. So we can, with these parametric registrations, we can just drag and drop, kind of like that. So that looks about right. Let's look at the side view. Let's go up. Yeah, something like that looks about right. That looks good. Yeah, so this isn't great because all we're doing is dragging and dropping. There's probably some rotation. We can do a little bit of rotation here. So if we do something like that, it might take a second to do it. This is a, I rotated the wrong way. We might want a -1 to rotate there or something to try and get it a little bit better. We can drag and drop again. Yeah, that's a little bit better. Does this look fine? Yeah, it looks fine. Okay, so this is probably fine. We're just doing this by hand. It's really nothing special. We just need to get something that's close enough. So I think that's close enough. So we're going to close out. You'll see here in this top part of the window, we have rigid parametric. So that's our initial transform. So this will show all transforms can be written out in text. There's always a short text representation of any transform you do. And so this is the current one, and you can copy it up there or whatever you want to do. Okay, so we had our rigid. This was parametric. So this was us dragging and dropping and moving these sliders. Let's switch to do a rigid but point-based. So let's see if we can get this a little bit better instead of just looking by eye, of selecting points. This will load for us. It might take a second. This is a 10-year-old laptop with no GPU that I'm running this on. Okay. And it's also even slower now because I'm recording my screen, which slows it down. Okay, so this is what it looks like so far. So what we want to do is we want to select points that are the same cell in the red versus the green. So the green is our movable and the red is our base. So like this pair of cells, that's a good one. So what we do if we want to add these two cells as paired points, we can click add new point. And so now the movable one will disappear. Now we just see the base. So what we can do is we can either go through and try and find the peak point where this is and click on it. And if we left click, it'll put a point right where we clicked. But if we right click, it'll try and find the maximum location nearby. So I'm going to usually right click on things because then it'll find the peak and we don't have to scroll through the planes to try and find the peak location. Okay, so we've paired those cells. It's usually a good idea to pair a couple, usually pair one in each corner. So the top and the bottom of each of the four corners, roughly speaking, tends to give good results. So let's see, let's flip on and off. Oh, let's do this one. This one looks good. Okay, and we can scroll in and out and make sure, yeah, it looks good. Okay, what about over here? Let's try another one. Ooh, these are nice. Let's do those. There we go. And now let's do one more towards the top up here. Maybe like, how about these? Those look nice. Okay. Now if we go down here, let's try another one. Let's do the bottom first. I don't know, this one looks fine. And then let's do maybe further up. Let's do these. Okay. We don't actually need this many points for a rigid. We really only need a couple for the rigid, but I'm adding a couple more just so you can see how it's done. So there's some more, and let's do one more down here. And sometimes it's nice to have a few extra points if it's not too hard. It's pretty easy here. Okay, so now we've got our points. We can hit perform transform, and we can wait a second for my 10-year-old laptop. And here we are. So it looks, it doesn't look great. I mean, look over here. Like, those aren't aligned very well. Yeah, these aren't great. And probably the reason for this is it's just not an appropriate transform because we're using a rigid. And maybe there's a little bit of non-rigidity here. So let's stop this. Let's instead of doing a rigid, let's do an affine transform. So you can see here our transform was updated. So we had rigid parametric, that was the first one we did, and now rigid. So it's great. But I don't think a rigid is appropriate. We probably should have done an affine instead. But we've also already selected these points. We don't want these points to go to waste. So what we can do is instead of having to reselect all these points, we can convert the transform. So convert a previous point-based transform. So we're going to convert our last transform, which is rigid. We're going to convert that to an affine. So that's where we get rid of this and we replace rigid with an affine, but we have all the same points. So let's convert it and let's see what that looks like. Okay. This doesn't look bad. Yeah, look at that. Those seem to be on top of each other. We can flip back and forth. Yeah, it looks pretty good. Let's see down here. These all look fine. Let's see. Yeah, I'd say that's fine. Okay, so we've aligned the z-stacks. And if we close out, if we look at the transform we have, we can see now it's affine instead of rigid. And we have all the same points. We didn't even need to add any new points. So now that we've done this, we can save. So let's save. So save to graph is if you want to just add it to the graph, but not save the graph to the disk. I'm going to do this for right now because I have the master file that I'm going to upload for all of you, so I don't want it saved, the answer is saved to the disk. So I'm just going to save it to the graph without saving to the disk, but you might want to write it to the disk if you're trying this because you can always re-download the file. There's also save to disk over here, which is where it just saves a copy of the transform itself. It doesn't associate it with the graph anymore, which can also be helpful. And if you just quit, the return value of this function is going to be the transform that you found. So you can do this and assign it to a value and not even save it to the graph if you don't want to. There are a couple other options on here that might be useful. Flip along the z-axis can be useful sometimes. You just flip your image upside down. View can be useful. Edit previous transform is if, suppose we wanted to add more points to this affine, we can just click this and it'll open up the viewer again for us to add points. Undo just undoes our last action. Remove previous transform deletes our last transform, so it'll take us just down to rigid parametric. Yeah, and then we'll talk about some of these other buttons in a bit. So I saved it to the graph. Let's do it again, just make sure. We'll quit. Great, so now what we can do, we can visualize the graph now. And oh, look at that. We now have a connection between the daily z-stack and the reference z-stack. Great. So now our graph is almost fully connected. I'll show you this right now before we do the last one. So if you've worked with Napari viewers before, we have a version of it's basically the same viewer Napari object if you've worked with this before, except for it allows you to pass in graph objects. So if we just do graph viewer something equals c8.gui dot graph dot graph viewer for graph G. So this will open us up in a Napari window. and then we can add things to it. So gv.addImage. So this is a standard Nepari syntax for a Nepari viewer is add image, but instead of passing a actual image to it, we can just pass the name that we want. So for instance, reference zstack, and it'll add it. So you can see here's our reference zstack. We can add image, or actually I'll show you. So the planes before were directly registered to the daily Z stack, if you remember. I'll show you here if we do like, I don't know, plane 4, and maybe plane 6 or something. So now you can see it. Oh, and the Nepari does this. I have to additive. Let's color it. I don't know, what should we make the planes? Let's make the planes red. Okay, and let's make this green. Okay, so now if we go through, we can see, oh, the planes they need to be contrast adjusted. Okay, something like that. So this is all standard Nepari now. But yeah, you can see now if we can flip it on and off. So now the plane is also registered to the reference stack, even though it was never directly registered to it, because they're even different sizes. Look at this; it goes off the side because the Z stacks were in slightly different positions. So even though we never directly registered this, since it was registered to the daily Z stack, now it's also by extension registered to the reference Z stack. Okay, that's enough of that. Now let's do. Now let's register this section. So this will be the fun part. So if we do this. Okay, so we're going to put, so before when we did this, we just put strings representing the nodes. Now we're going to do tuples. And these tuples will allow us to move things around together. So we want the red and the green channel for section 2. So we're going to align section 2 green. Like that. And then for the reference, we also want the red and green. So something like that. Graph equals G. And then transform. So as our starting position, we're going to use section 1 green because this one in the file I gave you was already aligned. So that'll give us a starting place. And on our references, we're going to add it as a reference too. Okay. So let's see how this goes. Okay, so so what we see up here, so this is our starting transform. So this was the transform we needed for the existing one, because this is our starting place. So let's start with a rigid parametric. It's usually a good place to start. Nothing beats drag and drop. Okay. So we can see, so here's our section. Our green one is the one we want to align. Blue is the reference, and red is the reference stack. So this also includes both red and green channels. So let me turn off some of these for a second. So this is the green part of the reference stack, and this is the red part. So the green is gcamp and the red is dtomato. And so here in the green, that's the gcamp. Here's the dtomato. And then here's our reference. So let's turn these on. Let's turn on only the gcamp ones for now. And so we can just drag and drop, hold Control Shift and click and drag. We can get roughly there. Something like this. Now let's switch to the side view and let's move this down so you can see the blue here and the green intersect with each other. So they're in the same plane. And now, oh, here, we can even just see it. Look at that. How easy is that? Right there. So you can see now that they line up. Well, they line up here. They start to diverge a little bit down here because, again, we just use this as a starting transform. We still have some work to do, but it looks pretty good. We can see where all of them are. Okay, so this gets us to a rough, close-ish place. So now that we're here, we're going to do a point-based. I'm going to start actually just with the laminar affine. So this is an affine, but it doesn't have shear in the thin directions of the section. You can read more about this either in the paper or in the documentation. Let's see. Okay. Here we go. So here's what we've got. Let's disable our reference right now, and let's actually turn off the. We probably won't even need the D tomato, to be honest. We won't even need that red channel. Okay, so here's our two sections. Let's just find a few cells. So like, I don't know, this one looks good. Looks good. I'm right-clicking each time, by the way, so I don't have to actually find the exact correct point. It just makes things a lot easier. Maybe what? I think these are the same. Let's do those. And then I'm scrolling a little bit to make sure that it actually did find the right place, and it usually does. Let's go down here. Oh, this is a good one. There. Yeah. And then let's see. Maybe one up here. Oh, what's a good one? Maybe this and this. Do it. Okay, no. So here's a good example. So it got the point that it got this one wrong because there's this bright cell next to it. So what we're going to do is we're going to delete it. So you can just hit remove point down here and just click on it. If you click near it, it'll be fine. As long as you're nearby. Okay, let's do this pair instead. So this one and this one. Did it find the right one this time? Oh no, it didn't find the right one either. Okay. Remove point. There we go. So now I'm going to demonstrate the left click. So here I'm going to find the center. I guess the center of the cell is like right here. So I'm going to left click this time. Okay, so now we have a handful of points. It's probably good enough to try our first transform. So we'll perform transform. And what this will do, so okay, that looks better. And we can iteratively go through this and work our way out, because once we align a couple, it'll make it easier to align them a little bit further away. So now we can go a little, okay, so like over here, like this is a good one. That's a good pair. Let's just perform. Okay, so now we have a few more. Okay, see, and then that makes it easier to see these. So like this is a good one. This pair. Yep. Okay, now we can even work our way over here now. Ooh, fancy. Okay. This and that maybe. I think are good. Let's see how that looks. That looks pretty good. Oh, maybe this pair is good. Nice, beautiful. Okay. That looks pretty good. Let's turn up the background here. Make sure. See, there's some of these in the middle that I'm not quite satisfied with. Look at these. These aren't very good. It's kind of hard to align them properly because it's under a blood vessel. There's a big black spot. If you look at here, I'll turn off the green so you can see. So like all of this is just under blood vessels, so we can't see it very well. And as a result, we don't get great alignment here. So some of this isn't very good. Like this isn't very good. Let's see if we can get this better. I don't think we can. I think we're going to need, yeah. So this is where the nonlinear piece comes in, because this isn't good enough. It's not very good. or this one, or any of these really. They're just not very strong. Let's grab one over here. Just while we're here, might as well. Yeah, okay. So we're going to need to go nonlinear for this section, which is fine. We have to do that for most of these sections because, I mean, they're mounted on a glass cover slip and then they're 50 microns thick, so there's some warping that goes on. Okay, but I think this is about as good as we're going to get with the affine transform. So let's close out of this. Come back to here, and you can see now the text representation of this. We have all the points that we paired are in this text representation. This is also, you can see, printed to the terminal each time. So if it ever crashes or something like that, you can always just copy and paste from the terminal. And this text representation is all valid CASTalign code. So you can just copy and paste this into a new Python session, and you have your transform back. So that's why we can copy up here as well. Okay, so we did our point-based laminar affine, and it was fine, but it still needs to be better. So let's do a triangulation. So one thing we could do is we could start from scratch. We could click on this laminar triangulation, and we could start and we could do our triangulation and select a bunch of new points. Or what we could do is we could seed it with the points that we already have with the residuals of the affine transform. Because when it's an affine, we have more points than we have degrees of freedom. So we're going to have some errors. So let's use those errors as a starting point. So what we can do is, instead of saying convert, because we don't want to throw away this previous transform, it was already pretty good, we want to extend. So extend is where you use the residuals of the previous one as a seed for the new one. So we're going to extend with a laminar triangulation. So we do this. Again, my 10-year-old laptop running screen recording software, not having a GPU. Okay. So now we have this fit. So let's see. Oops. Let's see how it looks. Okay. So here's the nonlinear. Let's turn off our reference. Let's turn off our red channel. Yeah, it doesn't look bad. So capture. Yeah, so this stuff in the middle that wasn't being fit before is now being fit okay. Got these ones on the side. Those we can toggle on and off. Yeah, that all looks pretty good. Let's go down here and toggle on and off. Yeah, I'll take that. It's pretty good. Could be a little. Let's do this. I think this could be a little bit better. I mean, you could sit all day and make this better. You don't need to. Let's just do this quick. But yeah, okay. So we'll add one more point here, and it looks like it's fine. And we can always, let's check with the dtomato. Okay, so now we have just the red stacks turned on. Yeah, and it looks pretty. Oh, this could be better over here. Let's add that as a new point. Okay. And up here, how does this look? Oh, it doesn't look bad. Let's turn down the contrast. Let's flip back and forth. Oh, this over here doesn't look so good. Yeah, I mean, now we're just getting to these tiny refinements. And this is, I mean, this is all already good enough to work for in vivo to ex vivo cell matching. But we might as well, if we see him, just fix him. Okay, that's better. So that looks fine. What about down here? Looks fine. Let's look at this side view. looking for something that looks mostly smooth. Yeah, it looks pretty good. It looks pretty smooth. I don't see any rough edges. Yeah, I'm happy with that. Okay, so now we have done this alignment. Cool. And we can, let's save it to the graph. We can also view it. So let's just look at it in the viewer and see what we did. Okay, and let's do a 3D rendering because those are fun. Okay, so here's our reference line. Let's turn off the red channels. So here's what we aligned in green, and then in blue was the reference one that we had. And here we can see the referencey stack in red, and all of those beautiful layer 5 pyramidal neurons in red, blue, and green. And if we can add, let's actually, okay, so let's quit. Let's actually go back to what we did before. So we had this graph viewer, right? And so we're going to add to the graph viewer, let's add the referencey stack again. Let's add plane 4 or something. And then let's also add our, what did we call it? Section 2. Section 2 green. Let's add that as well. We'll add all of these to the viewer. Just for fun, and then we have to color them. Let's section 2. Let's make that blue. Let's make the plane red and the Z stack green. I apologize if you're colorblind. Okay. Oh, and this again. Why doesn't Napari give correct contrast limit bounds? Yeah, there we go. Okay, so now we can see all of these registered together. So now our imaging plane and our ex vivo section, which we never registered together, we can turn off the background. And now we can flip back and forth. And we can see that they're registered to each other, even though we never directly registered them. And yeah, go through just like that. And again, you can see the big area here that falls out because of the blood vessel. We can't see it there. But yeah, flipping on and off looks registered to me. And yeah, and just for fun, we can do the 3D view. Let's turn on the referencey stack. And so there we have the imaging plane in red, and then in blue we have the section we just registered. And then in green we have the referencey stack. And if we want, we can add another plane. And here's our new plane. Oh, Napari, come on. What did we put it in red, I think, right? Red. And we still have to, adjust that contrast. There we go. Yeah, and there we have multiple imaging planes, multiple two-photon imaging planes, all registered with our Z stack and registered with our our ex vivo, image from the confocal microscope. Yeah, so there you have it. I hope this was useful in helping you align stuff, and good luck with your experiments.